would like to thank the organizers for the opportunity to speak to you today. Unfortunately, I can't be there in person due to some family constraints, but I'm happy to be able to share with you our work. So this work was motivated by a theoretical paper published by Albert Einstein in 1907 called Theoretical Observations on the Brownian Motion. In this paper, Einstein revisits Brownian motion from his 1905 paper, which is most famous, where he predicted diffusion. But Einstein realized that at short time, there's a problem with diffusion, that it gives an undefined velocity and undefined kinetic energy. And so he corrected this in 1907 and predicted that at short time, the motion must be ballistic. That is, there's a smoothing essentially of the Brownian motion. Instead of being random at all time scales and length scales, it actually becomes smooth and well-defined. And he coined the term instantaneous velocity of Brownian motion, which is essentially ballistic motion on timescales shorter than some characteristic tau sub p called the momentum relaxation time. To give you an idea, for a 3 micrometer silica microsphere at 300 Kelvin, that RMS velocity is 0.4 millimeters per second. If we want to measure this with about 10% uncertainty, that requires a very high temporal and spatial resolution, 100 nanoseconds in water and 4 picometers in spatial. That refers to the center of mass motion of the bead. In air, it's simpler, 0.5 microseconds temporal resolution and 0.2 nanometers in spatial resolution. But if you could measure that, then what Einstein predicted was very simple. He said that you should see the average kinetic energy is equal to, in one direction, to 1/2 K Boltzmann T, which is known as the energy equipartition theorem. And this simple result was predicted in 1907, but he challenged in his paper, a 1907 paper, he challenged us to measure the instantaneous velocity of a Brownian particle. And in fact, he also said that the experiment is impossible, at least for ultramicroscopic particles. That statement was true for over 100 years until now, until recently. Let's move forward to 1970 with the work of Art Ashkin, who invented the optical tweezer, which is used widely in physics and in biophysics and biology. The most common trapping scheme is a single beam gradient force trap, which takes a microscope objective and focuses it to a very short, over a very short distance to a small spot size and can trap little particles in water. We wanted to trap in air because that's an easier starting point. So we used 2 beams instead of 1 because we had to balance the scattering force, and by having 2 counterpropagating beams that accomplishes it. And we aligned them precisely, and we could image the motion on a quadrant photodiode using a second beam in the green. We could also simultaneously look at the scattered light on a camera. But let's go back to the quadrant photodiode for a moment, because that's an essential element. And typically, this is something you can buy. It is a photodiode that is segmented into 4 quadrants, and one can measure each photocurrent separately and take them, either add them or subtract them. This is a very common and excellent device, but it is limited in bandwidth to about 100 kilohertz, at least at the time. And so with a new idea, we developed a much faster position-sensitive laser beam detector, which sped up the measurement by about a factor of 1,000. That was reported in 2008. The idea was to separate the functions of wavefront splitting and photodetection. We did that by making a bundle of about 1,000 multimode fibers and feeding in a laser beam shown in the upper picture from the right. And we split it off into 2 bundles where the upper half of the beam goes one way and the lower half goes the other way, and then focused them onto fast photodetectors. This essentially separated the 2 functions, and we immediately saw this big factor of improvement. Since then, we've used a simpler method, the D-shaped mirror, which accomplishes the same thing, but we're actually coming back to the fiber setup for other reasons. When we did this, we could measure the mean squared displacement of a microsphere shown on the vertical scale in nanometer squared and on the horizontal scale in time in seconds. And what we saw was taken at two different pressures, atmospheric pressure shown in red and lower pressure shown in black and the noise shown in blue. We see that for short times, our measurements don't depend on pressure, and we see a slope that corresponds to ballistic motion. Diffusive motion has a smaller slope, a factor of 2, and it is shown for reference in the dashed lines. It also is pressure dependent. In longer timescales, we don't see diffusion simply because the bead is trapped. This is the same picture, but on a linear scale, and it clearly shows quadratic behavior as predicted. This is the raw data of one run, and we can see on the left side in red is the data taken for atmospheric pressure, and we can see the traces. In A is the direct trace that we measure, and then we derive from that in C the velocity. And this was the first direct measurement of instantaneous velocity of a Brownian particle. When we measure this repeatedly, many, many times, we get a distribution of velocities, and we plot them here shown on a semi-log plot, normalized counts as a function of velocity. And what we see is excellent agreement between our data and the Maxwell-Boltzmann distribution, which says that the bead has the same kinetic energy as a single air molecule. And this was the first direct test of the energy equipartition theorem for Brownian motion. There are no adjustable parameters here, so this is an absolute measurement. This was reported in a paper in Science in 2010. Now, we did this in air, and air is easier than liquids because the density is much lower. So it was natural to ask, what about liquids? Can we do it there too? Well, that turned out to be harder, and we had to actually find new materials, both bead material and fluid. Instead of silica, we used a higher density glass called barium titanate, which has a higher density and refractive index. For a fluid, we went from water to acetone, which has lower density and much lower viscosity. And together, we were able to actually resolve the instantaneous velocity of Brownian motion in liquid, which was reported in Science in 2014. This data shows a detailed measurement of the distribution taken very high statistics and over many orders of magnitude in 2015, and also very good agreement. This was done barium titanate and acetone. So excellent agreement with the equipartition theorem. The only thing here that you don't see is that in order to get this fit, we had to use an adjusted mass, which is not the bare mass, but something called added mass. And I'll come back to that at the end of my talk. Now, if we consider the equipartition theorem and we turn it around and we say we can measure the velocities, and we suppose the temperature is fixed, in our case, room temperature, then by measuring velocities, we can essentially determine the mass of the particle. And we did that, and this was reported in a paper published in 2020, weighing an optically trapped microsphere in thermal equilibrium in air. This result was interesting for several reasons. It showed that we could actually, a very fast determination of a mass of a particle, which is, I don't know any other way to measure this on such a fast time scale. And this could be useful for a number of things. For example, to study heterogeneous nucleation, where a particle accretes mass in time. And this occurs, for example, in ice nucleation of dust particles in the atmosphere, and is used for cloud seeding to create rain. In fact, that process is not very well understood, and it's possible that with our new methods, we could optimize the morphology and the surface chemistry of our small particles to optimize the nucleation, and thereby could have an impact on cloud seeding. The next direction that we followed was to say, could we use our methods to measure sound very precisely? And to do that, we We got rid of the bead, so we no longer used an optical tweezer, but we kept our detection method, which is the split beam, and we added another method called a Sagnac interferometer. And the combination of the two was reported in a paper just 2024. Sagnac witness laser deflection is an ultra-sensitive acoustic detector. In fact, we compared our results with state-of-the-art acoustic detectors that we bought, and our method far surpassed that. So we have a quantum limited acoustic detection actually working. And what is this good for? Well, two directions, and we're pursuing both of them in collaboration. One is ultrasensitive acoustic detector for dark matter searches. This is done in a bubble chamber, and this is a picture of the Pico 60 machine at Snow Lab, where they're searching for dark matter. When a dark matter particle comes by, interacts with matter, it would nucleate a bubble in the chamber, and that expanding bubble, it creates an acoustic wave. And we're in discussions with the Pico collaboration, which are building their next generation experiment. Another direction is ultra-sensitive acoustic detection for medicine. And in particular, one example is pinpointing the stopping of high-energy protons in cancer therapy. Shown is a picture of a proton therapy machine at MD Anderson Cancer Center in Houston. So to summarize, we observed the instantaneous velocity of Brownian motion in air and liquids, thereby realizing the challenge by Einstein from 1907. This was all in thermal equilibrium. We use these methods to weigh a Brownian particle in situ, which has applications to potentially to heterogeneous nucleation, perhaps even cloud seeding. We developed a new method of sound detection, not with the tweezer anymore, but with just laser beam deflection using a Sagnac interferometry. And we observed quantum limited sound detection, which could be applied to medicine in both for cancer detection, cancer therapy, proton therapy, and other medical imaging. In the future, we want to work on several topics. One of them is we still need to resolve the added mass effect. Although our measurements were consistent with the added mass, we can't completely conclusively say that we saw it because there was some uncertainty in the density of our trapped beads. We are working to address that, and hopefully we'll be able to report that effect soon. We also want to observe the onset of viscosity in time. This will require going to timescales that are even shorter, down to picoseconds, and we intend to do this with a picosecond pulse laser that we now have operating. This would be very important fundamental fluid dynamics because right now viscosity is just added by hand, so to speak, to the Navier-Stokes equations. And finally, we'd like to study non-equilibrium phenomena at short times. I'd like to end here and just thank and acknowledge all the members of my group who are working on many other projects that I don't have time to talk about that constitute about 80% of our effort. I highlight Jason Boynovich and Cole Thuman here. They are the team members that are working on our short-time Brownian measurements and are here with you at this conference. And they have a poster and a talk by Jason following this talk where we will report new and unpublished results on short-time Brownian motion. Thank you for your attention.